What I would like to do is just review a little bit of acid-base chemistry. You may have heard from ne'er-do-wells that you would never need any of the chemistry you learned in high school, but that was a total lie.
What does the H+ symbol mean?
H stands for hydrogen, which is element number 1 on the periodic table. Now, when hydrogen loses its electron, it is just one lonely proton. So when we say H+, we're referring to the hydrogen ion, and as shorthand, we just call it a proton.
What is an acid? What is a base?
In aqueous or water solution, an acid will give up a proton, becoming what is called its own conjugate base. In contrast, protons jump on a base, which will convert it into its conjugate acid. Now, it might seem counterintuitive that a proton jumps on an uncharged base, but just remember that protons are sort of naughty little Casanovas. They don't like to be alone, and if there is a base nearby, they will jump on it. This has nothing to do with the term base jumping, which is a completely different thing. Now, looking at these two equations, you might say, this looks like just the exact same equation, except one of them is backwards. But look again, acids and bases in their natural states have no charge, or we call them being deionized. Their conjugate bases and acids have a charge. So the acid in the top equation there is not the same as a conjugate acid in the bottom equation. If that's confusing, another way you can think about it is that an acid with its extra proton has no charge, but a base with its extra proton is charged. Now, the important part of this acid-base stuff really is the charge business. The thing here to concentrate on is ionization.
¿Qué es ionización?
Ionization is the process by which an atom or a molecule acquires a negative or positive charge. Ionized means there is a charge. That can be positive or negative. Deionized means there is no charge. Other ions you already know are things like sodium, potassium, and chloride. These are all things that have either positive or negative charge.
Why should I care about ionization? I don't know. Let's ask the professor.
So this ionization is a huge deal when you talk about pharmacology, and that's because the cells in your body have enclosing cell membranes made out of lipids. You may recall that plasma membranes are made out of phospholipid bilayers, as well as cholesterol and some other fats. Now, in order for drugs to be absorbed across these barriers, they have to be soluble in lipid. So drugs that have no charge on them, that are deionized, are more lipid soluble and therefore can pass through membranes. On the other hand, to dissolve inside a cell, or to be carried around in the bloodstream, or to be excreted by the kidneys, molecules must be water soluble. So charged or ionized molecules are water soluble. So the take-home message here is lipid soluble, deionized, water soluble, ionized.
How can one drug be ionized and deionized at the same time?
Now, weak acids and bases easily switch between the ionized and deionized states depending on the pH of the environment. That's an excellent question, Dido, the cat. pH is defined as negative log H+, where H+, this is the concentration of free protons in any solution. So if you stick a pH detector, which is called a pH meter, into any solution, that detector is only looking at the concentration of free protons, just the free protons, the concentration of these H+ ions floating around in any solution that you care to measure. When measuring pH, you don't care what other stuff is in that solution. It doesn't matter which acid it is, if it's sulfuric acid, folic acid, amino acids, doesn't matter. pH is only measuring the free hydrogen ions, the free protons. A low pH solution is an acidic solution because there's lots of protons floating around. A high pH solution is basic because there are relatively few protons floating around. So pH less than 7 is acidic, pH greater than 7 is basic.
Buenos días. Pues dígame, ¿cuál es la diferencia dentro de un ácido fuerte y un ácido débil?
How strong an acid or base is depends on how completely it dissociates in water. So a strong acid like hydrochloric acid is almost 100% dissociated into hydrogen ions and chloride ions when you put it into water. Now this works out very well in the stomach where the acid actually is hydrochloric acid because the stomach wants lots of free protons floating around inside of it, all ready to jump on things like bacteria and proteins and other kinds of bases. Now, most drugs are either weak acids or bases, which means that they flop more easily between their ionized and deionized state, that is, they're with an extra proton and without an extra proton state. They flop around between those two states well in aqueous solutions that are found in the body. Now, which state the drug finds itself in depends on the pH of the solution, as well as the pKa of the drug and the concentration of the drug.
What is pKa?
The pKa of a drug is defined by the Henderson-Hasselbalch equation, where the pH equals the pKa plus the log of the conjugate base over the acid. HA here is the concentration of the uncharged protonated acid, and A- is the concentration of this conjugate base. Remember, pH defines the number of protons free in any solution. It doesn't have to do with the molecule. The pKa, however, is specific to each molecule. Now, you may remember that log of 1 is 0. So, when the amount of acid is equal to the amount of conjugate base, that log term cancels out. So, the pH at which this happens is equal to the pKa. All right, so the pKa is different for every drug. That's their pKa. That refers to each particular molecule. It's not the same as pH, which refers to just the amount of free protons in any solution.
Can you give me a real-life example?
All right, yes, let's do an example. So imagine we have some aspirin, which has the molecular property of being a weak acid. It has a pKa of about 3.5. Now, if it is an acid, it means that the form with the extra proton is not charged. So here's an image of that. On the left is the aspirin with the extra proton. On the right is the conjugate base of that aspirin. Just to make things easier, I'm going to make a cartoon version of this same thing. So let's give this to a patient. Here's 24-year-old Joe. He has a headache, and I'm going to give him 2 aspirin to take PO for his headache. Aspirin is a weak acid, so in plain water solution, it exists in 2 forms, an acid form and the conjugate base form. However, the stomach is not filled with plain water. It is also filled with hydrochloric acid, and the pH is low, depending on the time of day, whether or not there's a meal present. But, at the low end, the pH of the stomach is about 1.5 to 2. A little more acidic than Diet Pepsi, something like that. Now, when the pH of a solution is low, it means there are lots and lots of free, notorious Lothario protons, right? These protons just want to jump on bases. So all these free protons are floating around, and they want to join up with any molecule that they can find. Now, protons see the 2 forms of aspirin as not just the acid and the conjugate base version, but rather as the taken and not taken versions. The conjugate base is something that is available for those free protons to jump on top of. So let's look at the stomach. The moment the aspirin hits the stomach's acidic solution, every ionized aspirin hooks up with a proton, which leaves Joe here with a stomach full of this stuff. Now you'll notice there's some free protons, but almost every aspirin is occupied by an extra proton. Now, almost every aspirin molecule is deionized and is therefore lipid-soluble. And in fact, if you do the calculation, which I'll do at the end of this video, in stomach acid, there are about 100 times as many deionized aspirins as ionized aspirins. So almost all of the aspirin can be easily absorbed. The upshot of this is that we can give acidic drugs fairly easily as a PO drug, because when they hit the stomach, the solution of stomach acid, which is full of free protons, will turn that acidic drug into an uncharged molecule that is now easily absorbed across the stomach wall. Once that acidic aspirin leaves the stomach, because it's gone through the wall of the stomach, it finds itself in the bloodstream. Now, the bloodstream has a pH of about 7.4, just a little bit more basic than plain old water. Now there aren't nearly as many protons floating around, so the protons that are hooked up to our aspirin will run off to hook up with some other molecule that's floating around. It doesn't matter what it is, some kind of a base, bicarbonate, protein, whatever. I've drawn these other molecules, these other bases, as little dark squares in this picture. Protons don't care particularly what they bind, they just want to hook up with a basic molecule. So now in the bloodstream, Most of the aspirin exists as its conjugate base form. And in fact, at a pH of 7.4, there are almost 8,000 times the number of ionized aspirin molecules for every deionized aspirin molecule. So now these aspirin molecules are easily carried in the bloodstream, where they can be carried to their site of action, or they can bind a receptor, or they can be excreted in the kidney. What do you think happens to aspirin absorption when patients take over-the-counter antacids? For instance, our patient Joe, if he had just taken several Tums or some milk of magnesia, that would change the acidity of the stomach. So what will that do to the absorption of the aspirin? Well, what about basic drugs? Well, if we want to administer a basic drug, we have two options. We can either administer a conjugate acid of that basic drug. So, for example, a basic drug like propranolol would be poorly absorbed in the stomach, but its conjugate acid in the form of propranolol HCl is absorbed just fine. Another thing we can do is to just administer the drug some other way, parenterally or topically, IV, inhaled, whatever, and just bypass the whole business in the stomach. Or you can just wait for it to be absorbed by the intestine. The take-home lesson here is that the acidic and basic properties of the drug molecule itself will determine how fast it is absorbed, how we can administer it, and how easily it will be excreted by the kidney. Novocaine is an old-fashioned drug that was popularly used by dentists to numb up gums before dental procedures. How might they have improved absorption of Novocaine when they administered these drugs to their patients? All right, I hope this helped you. Remember, a quick way to check your work is that acids are deionized and best absorbed through tissues in an acidic environment, and bases are deionized and therefore best absorbed through tissues in a basic environment. See you in class.